I'll be discussing the stability analysis of a tethered airfoil. So today's presentation will be broken up into four main parts. First, I'm going to discuss the model development, so assumptions and the various forces that the tethered airfoil system is going to experience. Then we're going to go into deriving conditions for stability for both a straight tethered case and a catenary case. And then I'm going to go through some simulation results that we have, and then draw some quick conclusions. So this is a schematic diagram of our system. As you can see, there is a kite with some mass attached to a tether of some mass and a length, and it's attached to a mooring point O. And it's in a wind field at some angle, and there's an angle of attack, and the inclination angle of the kite is phi k. And there's some basic assumptions that we make. All these are important, however, the most restrictive ones are probably the first one and the second to last one right here. We assume that it moves in the YZ plane only simply for simplicity in our calculations. Obviously, in a wind field, we might have some kind of induced lateral motion, but for the time being, we ignore that and just look at the simplified case where it's only moving in 2 dimensions. And this assumption, the one where we're keeping a constant angle of inclination with some control system, that would be covered in a different paper, something dealing with angle control and maneuvering. This is more a stability analysis paper, so we're just going to assume that there's a control system and not worry about it too much. So the aerodynamic forces on the airfoil are very simple. There's your standard run-of-the-mill lift and drag formulations that you can find in any fluids textbook. And furthermore, the coefficients of lift and drag are also pretty cookie cutter. They're derived from fin airfoil theory. So our equilibrium position, we do a sum of forces on our system. This is just static equilibrium, so we sum the forces in the y, sum them in the z, set them to 0, and then go about our analysis. It's also important to note that the center of mass and center of pressure on the airfoil are assumed to be at the same point. And this can be done because we assume that there's a control system, and that allows us to manipulate that and make this kind of calculation easier for us. So some quick takeaways. At equilibrium, you have equal and opposite forces in the y direction and z direction. We assume that the cable takes the shape of catenary, and that's given by that equation. The various parameters such as a, q, and h, those just define the geometric configuration of the catenary. We assume that the length of the tether is a constant, and that's shown by just a simple line integral. And since the tension in the catenary cable is tangential along this length, at either endpoint we can establish a boundary condition by looking at the vertical and horizontal forces. And doing that, we can get an angle that the endpoints assume, and that'll be important later. And then moving forward, we can solve for equilibrium, lift and drag, and from there we can solve for the equilibrium position of the kite itself. So that brings us to 2 different stability analyses. One is the straight tether assumption that I mentioned a little bit earlier. This is valid when the wind speeds are high. And so as the wind speed increases, your lift and drag increases along with it and stretches the cable out, eventually making it straight enough so that it moves in roughly a 1 degree of freedom type of motion. And this is nice because it's simple to analyze and it gives us analytical results. However, a more realistic and a more realistic approach to solving this problem would be this catenary tether case, where this is more valid for lower to moderate wind speed, so that you have 2 degrees of freedom, so the kite can move up and down and left and right, for example. So the two degrees of motion are decoupled, just so long as the length of the tether remains constant. So first, let's take a look at the straight tether analysis. This is just a quick schematic diagram of the straight tether. So as you can see, we're going to just get a equation of motion using theta as our degree of freedom. This is the equation of motion. Like I said earlier, sum the moments about the mooring point O, and you get that. The lift and drag formulations are shown below, and it looks nice, but it's also nonlinear. So in order to investigate stability, we linearize the equation about some equilibrium angle, and then proceed from there. Upon linearizing, we get a classic second-order mass spring damper-like system, and we know that in order for that kind of system to be stable, we need to have the three coefficients have the same sign. So that means that if we solve for the coefficients that go along with delta dot and delta, we get these two stability criteria. This one corresponds to C, this one corresponds to K. We don't necessarily have to worry about the first one, which is the inertia term, because inertia is always positive. So moving on to the catenary case, again, we sum forces in the y and the z directions. And it's important to note that here we assume that the table at all times, even during transients, maintains a catenary shape. At equilibrium, that doesn't really matter, but it's just something to note. And upon linearizing and performing lengthy derivations, we can express the equations of motion in a matrix expression. So this is just a coupled mass spring damper system. And in order to get an insight to stability of the system, we can re-express it in state space. Excuse me. And if we find the eigenvalues of this 4x4 matrix, then we can get insight into the stability of an equilibrium point. So let's move on to simulations. These are the simulation parameters that we use. The two most important ones are, these two are initial and final wind speed. So we start off at 15 meters per second wind speed, just going in the y direction. There's no vertical component of the wind speed, it's just horizontal. And then after a while, we step instantaneously to 20 meters per second. And these simulations were run using FEA code, and the finite elements are the tether itself. So there's 10 line elements composing the tether. And those, the various motions of that tether will be shown in the following results. So these are the results for our straight tether assumption. In the upper left, we see a plot, a time history plot of the various angles of each individual element in the tether. So right here is the first equilibrium condition. This is where it reaches steady state in a 15 meter per second wind speed field. And then after a while, it jumps up to 20 meters per second, and we have a different tether angle. So you can see it makes sense. In a lower wind speed, you have a shallower angle, whereas in a higher wind speed, you have a higher angle. And that's simply because you have higher lift and drag components stretching the tether out. You also notice that this banding is a lot tighter than it is here. And this is the increase in angle of the tether shown here. So the initial condition places the kite somewhere in here, and the kite moves to here after it settles down to steady state in 15 meter per second wind speed. And then after the step change, it moves to here. So you can see that, again, with the increase in wind speed, there's a higher force on the tether itself, and it makes it more vertical as well as more taut. So just some quick observations. As I mentioned earlier, before the step change, there was a certain average tether angle that the tether assumed, and after it, it was a slightly steeper one. Intuitively, the force on the airfoil increases as the wind speed increases, and you'll notice that these two numbers roughly match these two numbers, and so that kind of shows that our straight tether assumption is reasonable, at least at these wind speeds. So these next two slides are going to delve into the two stability criteria that I talked about earlier. So for the coefficient C, the damping coefficient, over here, this on the left-hand side, this blue trace is CD divided by CL, and this is the instantaneous calculated CD by CL. So we go into our simulation, we pluck CD and CL values, divide them, and plot them. On the right-hand side is this red dotted trace. This trace is calculated from our expected values, those theta E's and beta E's. And those are taken from here. So before the step change, we use this one, and then afterwards we use the bigger one. And in order for this criterion to be satisfied, this blue trace needs to be above this red trace, so that it's greater than. So the conclusion that we draw from here is that for the first 200 seconds of simulation, the stability criterion is violated. Now going on to the spring coefficient K, again, the blue trace represents the left-hand side, and that's calculated instantaneously. However, in this case, we use not the calculated theta E, but we use the theta E that we got from our initial results. And then the red trace is the right-hand side. And as you can see here, the stability criterion is satisfied for all time. However, in the grand scheme of things, both have to be satisfied simultaneously in order for the straight tether assumption to be valid. So from here we can conclude that after 200 seconds, our straight tether assumption is valid, and beforehand, it's something else. So now moving on to the catenary case, this surface represents feasible equilibrium points that were calculated using the equations of motions that we derived beforehand. This might be a little bit confusing, basically what we're looking at here is all the equilibrium points that are possible given any mass of the kite in any wind field, and then the angle that the tether at the mooring end makes with respect to the horizontal. And this green line, green plane, represents 0. So what we're saying here is that we're going to only look at the points above 0 as quote-unquote feasible equilibrium points. And the reason that we do that is we want the tether to be off the ground at all times. So if that angle is 0 or less, the tether might be dragging on the ground, which would be fine if this thing is tethered off the side of a cliff or something, so the tether can go down and then come back up. But if we assume that this kite is suspended in the middle of a field, we want to maintain that length of the tether as whatever it was that we used. So we only want positive angles at the mooring side. And in order to investigate whether or not the equilibrium points here in this location are stable, what we're going to do is solve that 4x4 matrix that I looked at earlier for its eigenvalues. And if we have negative real parts, then we can conclude that those equilibrium points are stable. So what we did here, we kept the wind speed constant and then varied the mass of the kite over a certain range. And we chose it such that the mass of the kite, the combination of mass of the kite and the given wind speed would not ever bring the equilibrium points below this green plane. So for example, if I pick 10 meters per second wind speed, I would just go across here, and we can see that it will never drop below the green plane. And from here we can see that all the real parts are negative. So we can conclude that given some constant wind speed, we can vary the mass of the kite over some range, and we're still going to have stable, feasible equilibrium points. And this makes sense because in a spring mass damper system, you can increase the mass all you want, and that's not necessarily going to affect the stability of the system for the equilibrium points. Similarly, we chose to fix the mass of the kite and then vary the wind speed over some range. And again, we have a similar trend where the real parts are all negative. Granted, there's a limit to where we can go. If we have 0 wind speed, then obviously the equilibrium point's not going to be feasible. But as you increase the wind speed, the kite gets more and more stable, which makes sense because you have increased aerodynamic forces. So, quick conclusion, we derived some stability criteria for both the catenary case and the straight tether case. For the straight tether, we were able to get analytical solutions, but for the catenary case, we had to verify our findings numerically. And in the future, we'd like to analyze the stability of the system when we use it to harvest energy by reeling in and out from the base point, for example, and seeing how that reeling motion would influence stability. We would also like to investigate periodic orbits, so we'd like to relax that first assumption and let the kite move around in 3 space rather than 2 space. And finally, we'd like to just investigate general nonlinear behavior of this system. So with that, I'm done. Are there any questions?
Thank you.
No questions? All right, thank you very much.
Okay. Do you consider application to windmill or wind energy?
Yes, this paper actually stems from some previous work that we did with regards to extracting energy using a tethered airfoil. We did some preliminary stability analysis with that. What we did here, we just took away the energy harvesting component of it and just focused straight just on stability. We wanted to see if it's at all possible to get stability criteria. So, like I said, our future work will involve combining the 2 approaches so we can harvest energy and see if it's, like, what conditions we need to have for stability as well as energy harvesting.